Hello, sleepy soul. You have found your way here, to this quiet corner of the universe, and that in itself is enough. Whatever the day held, its weight, its noise, its endless demands, you can set all that down now, gently, right here at the edge of this moment before sleep. Tonight, we are going to travel somewhere remarkable. We are going to visit a world that has lit up the skies of every human being who has ever lived. A world so bright, so luminous, so achingly beautiful in the dark that our ancestors looked up at it and believed it must be a god. A world that rises before the sun and lingers after it sets, as though it cannot quite bear to leave the sky. Tonight, we drift together toward Venus. There is no hurry. There is nowhere to be. The world outside is already slowing. The sounds of the day are softening at the edges. Your breathing is deeper than it was a moment ago. Let your shoulders settle. Let your hands rest open. Let your thoughts, whatever they are, begin to loosen, the way a knot loosens slowly when you stop pulling at it. We are in no rush. Venus has been shining above this world for 4.5 billion. Long before there were telescopes, long before there were satellites or photographs or any of the instruments we use today to study the sky, there was that light, a single, steady, luminous point of white gold above the horizon, sometimes in the west after the sun had gone, sometimes in the east before the sun had risen, always beautiful, always impossibly bright, always the same. And people looked up at it and wondered. The ancient Babylonians kept records of it on clay tablets. The Mayans built entire temples aligned to its movements. The Romans named their most beloved goddess after it. And on quiet evenings all over the world, in villages and valleys and on the decks of ships far out at sea, ordinary people stopped what they were doing to look at it and feel, for a moment, very small and very peaceful. You have likely seen it yourself, perhaps without even knowing what it was. That unusually bright star low on the horizon that doesn't flicker, doesn't waver, just holds its light steady and calm above the darkening earth. That was Venus. Tonight, we will learn a few things about it. Gently, slowly, in no particular order. Some of these things will surprise you. Some of them will make you smile. Some of them, I hope, will carry you quietly down into sleep, the way a warm current in still water carries you without effort, somewhere soft and deep. There is nothing you need to do, nothing you need to remember. Simply let the words move through you, like light through still air. Of all the objects in the night sky, only the moon shines brighter than Venus. Think about what that means for a moment. The moon is an entire world, hanging close above us, vast and pale and full. And yet Venus, a planet nearly 100 million kilometers away, barely the size of our own Earth, manages on some nights to rival it, not because it is large, not because it produces any light of its own, but simply because of the way it catches the sun. Venus reflects light extraordinarily well. In the language of astronomy, the measure of how much light a surface reflects is called its albedo. A perfectly dark object would have an albedo of 0, absorbing everything, reflecting nothing. A perfect mirror would have an albedo of 1. Most things in the universe fall somewhere in the middle, rock and soil and ice, each reflecting a little, absorbing a little. Venus has an albedo of approximately 0.75. That means that for every 4 units of sunlight that reach it, 3 of them are sent straight back out into space. The planet is, in effect, a vast spherical mirror, wrapped in layers of bright cloud, polished by its own dense and restless atmosphere. Roughly 3/4 of all the light that falls upon it bounces back toward us. It is the most reflective planet in the solar system by a wide margin. And because of this, Venus is not just the brightest object in our night sky after the moon. It is bright enough on a clear night to cast a faint shadow on the ground. If you have ever stood outside in the deep countryside, far from city lights, and looked west just after sunset, you may have glimpsed that shadow spreading out faint and silver behind you, not cast by the moon, cast by a planet. Astronomers measure the brightness of objects in the sky using a scale called apparent magnitude. On this scale, lower numbers and negative numbers mean brighter objects. The full moon sits around a magnitude of -12. Our own sun sits at -26. Venus, at its most brilliant, reaches magnitude -4.6. At that brightness, it outshines every star in the sky. It outshines Jupiter. It outshines Mars, even when Mars is at its closest and most vivid red. On a clear night, Venus stands alone in its brightness, obvious, unmistakable, serene. And because of those famous phases, because Venus, like the moon, shows different illuminated shapes as it orbits the sun, even a small telescope will reveal its changing face. A thin silver crescent, then a half disk, then a full glowing ball, all of it distant, all of it luminous, all of it quietly beautiful. There is something calming about the constancy of Venus, because while the stars shift over the course of a night, wheeling slowly overhead as the Earth turns, Venus moves differently. It stays close to the sun. It rises before it or lingers after it, but it never wanders far. It is always there, predictable, familiar, holding its position in the early morning or early evening sky. And this predictability made it an anchor for our ancestors. Long before clocks and calendars, the movements of Venus were one of the most reliable ways to track the passage of time. Civilizations across the ancient world, in Mesopotamia, in Mesoamerica, in Greece, in China, observed it, recorded it, built their sacred architecture in alignment with it. To the Romans, she was Venus, goddess of love and beauty. And it is not hard to understand why, when you consider the image she presents. Warm and brilliant, glowing low on the horizon in the colors of dusk, neither aggressive nor hidden, but simply present, radiantly, undeniably present. To the people of Mesoamerica, the same light had another character entirely. The Aztecs associated it with Quetzalcoatl, the feathered serpent, a god of wisdom, wind, and the cycles of time. They tracked Venus with extraordinary precision, calculating its return with an accuracy that required centuries of careful observation. The Maya went even further. Their Venus tables, recorded in the Dresden Codex, tracked the planet's appearances and disappearances across the sky over a period of more than 100 years, aligned to the Mayan sacred calendar with a precision that still impresses modern astronomers. All of this from a single point of light in the sky. All of this wonder and calculation and devotion, sustained for generations, inspired by something no larger in the eye than a grain of salt. Because Venus follows the sun so closely, it is never seen at midnight. It rises with the dawn or lingers at dusk, and that in-between quality, belonging neither fully to day nor to night, gave it a double name in many cultures. In the morning before sunrise, ancient observers often called it the morning star. In the evening after sunset, the same light was called the evening star. For many ancient civilizations, these were believed to be two entirely separate objects, two different lights, serving two different purposes. It was not until philosopher Pythagoras, or perhaps even earlier, that someone made the quiet, rather astonishing realization that the morning star and the evening star were the same. A single world, following a single path, appearing in different places, not because it was different things, but because it was seen at different times from a moving earth. The same planet, the same light, two names for one wonder. And sometimes, rarely, but magnificently, Venus does something even more remarkable. When its orbit carries it directly between the Earth and the Sun, it can sometimes be seen from the surface of the Earth as a tiny, perfectly round, slowly moving that cross in the face of the Sun, a transit of Venus. These transits are extraordinarily rare. They occur in pairs, 8 years apart, but those pairs themselves are separated by more than a century. For most of human history, a person could expect to live their entire life without ever witnessing one. Perhaps their parents would not have seen one either, nor their grandparents, nor their great-grandparents. The last two transits visible from Earth occurred in 2004, and then again in 2012. If you were alive and had access to a filter or a telescope in those years, you had the opportunity to watch Venus, that familiar, brilliant point, transform briefly into a small, unhurried shadow drifting across the sun, taking about 6 hours to cross from one edge to the other. The next transit will not occur until 2117. There is something quietly moving about that. A slow parade across the sun, watched by human beings for centuries. James Cook sailed the Pacific in 1769 specifically to observe the transit of that year. Standing on the deck of his ship in Tahiti, watching that same small that we have watched. Edmund Halley, the man who calculated the return of the famous comet, urged the astronomers of his generation to observe the transit of 1716 precisely and carefully, knowing that by measuring the timing from different points on Earth, they could calculate the true distance from our world to the sun. Generations of astronomers, separated by centuries, connected by that slow black, and perhaps the most earthly, most human consequence of all this brilliance, Venus is, to this day, the single most commonly misidentified object in the sky. Police stations have received calls about it. Weather agencies have logged reports of mysterious, unmoving lights. Pilots have filed incident reports. Newspapers have run stories about strange glowing objects hovering above the horizon that turned out, every time, to simply be Venus. There's something charming about this. Not foolish. The planet really is startlingly, disarmingly bright, especially on a humid or hazy night when it floats low in the sky and seems to pulse slightly as its light filters through moving air. It does look, in certain conditions, almost impossibly brilliant, almost too bright to simply be a planet. But there it is, patient, unchanging, ancient, the evening star, the morning star, the shepherd star, the star of Ishtar, the light that lit the faces of every human being who has ever stepped outside and looked up at the western horizon as the sky darkened and the first point of light appeared. Venus, the sky above you tonight holds that same light. If you could see through the ceiling, through the walls, that same bright point that is hung above every sleepless person who has ever lived, that same pale gold radiance that the ancient Babylonians recorded on clay and the Mayans calculated across centuries, is up there now, in the dark. You do not need to look for it. It knows where you are. Let your eyes be heavy now. Let your thoughts drift a little further from the day. We have a long, quiet journey still ahead of us. So many more gentle wonders to unfold. But there is no hurry. We are traveling at the speed of Venus, slow and luminous, steady and ancient. Let your breathing slow. Let your body sink a little deeper. Long before anyone knew what Venus was made of, long before anyone could calculate its distance or guess at its temperature or imagine anything about its surface, people knew its rhythm. They knew it the way you know the rhythm of a familiar piece of music, even when you cannot name the notes. They knew it because they had been watching and recording and watching again, generation after generation, passing the knowledge between them like a flame cupped against the wind. The Babylonians were among the most careful. To the astronomers of ancient Babylon, Venus was Ishtar, the great goddess of love and war, of desire and destruction. She was not simply beautiful. She was powerful, and her movements in the sky were not decorative but significant, carrying meaning about what was to come, about harvests and battles, about kings and seasons. The Babylonians tracked Venus across a cycle of approximately 8 years. They observed that after 8 years, the planet returned to very nearly the same place in the sky, at the same time of year, appearing at the same point on the horizon at the same time of morning or evening. It was close enough that they could align their temple rituals to it, organizing their religious calendar around the planet's slow, reliable return. 8 years between repetitions. And in those 8 years, Venus would complete exactly 5 of its characteristic cycles. 5 disappearances and reappearances. 5 transitions from evening star to morning star and back again. The number 5. The number 8, 2 numbers that would come to mean Venus across the ancient world. in ways that were not entirely coincidental. Far across the ocean, in the rainforests and highlands of Mesoamerica, the ancient Maya arrived at something similar through entirely independent observation across many centuries. With remarkable precision, the Maya calculated the synodic period of Venus, the time it takes for the planet to return to the same position relative to the Sun as seen from Earth, as 584 days. The actual value is 583.92 days. They were off by less than a day, without telescopes, without computers, without any instrument more sophisticated than a straight stick driven into ground to cast a shadow, and a patient pair of eyes, and a system for recording what those eyes saw. The Maya built this knowledge into their sacred calendar. The 365-day solar year and the 584-day Venus cycle produce a combined repeating period of exactly 2,920 days, or 8 solar years or 5 Venus cycles. And they use this alignment, this slow interlocking of cycles, to determine the timing of important events, including, apparently, the timing of warfare. Certain Venus apparitions were considered auspicious for launching campaigns. There is something almost meditative about the patience this required. Generations of astronomers sitting with their observations, not rushing conclusions, letting the pattern reveal itself over years and decades, trusting that if they simply kept watching, the truth would eventually emerge. A slow science, practiced quietly in the dark. In 1610, a man in Padua pointed a small, imperfect telescope at Venus for the first time. His name was Galileo Galilei, and what he saw changed the way human beings understood their place in the solar system. He saw that Venus had phases, like the moon, which grows from a thin crescent to a full circle and back again as it moves through its orbit. Venus, when observed through even the simplest optical instrument, showed the same progression: a thin sliver of light, then a half disk, then a nearly full globe, then shrinking back again. This was not a small observation. This was profound, because in the model of the universe that the Church and many scholars of the time defended, the Ptolemaic model, in which everything orbited the Earth, Venus should not have phases like the ones Galileo was seeing. The geometry was wrong. If Venus circled the Earth, it could only ever show as a crescent, never a nearly full disk. But if Venus orbited the Sun and Earth also orbited the Sun, as Copernicus had suggested decades earlier, then the phases made perfect sense. Venus was a sphere lit by the Sun, and as it moved around the Sun, different portions of its illuminated side faced the Earth. In a quiet courtyard in Padua, by the light of a candle and the glow of a distant planet, the Earth was moved from the center of everything, not by argument, not by philosophy, but by the simple, patient observation of a crescent growing slowly into a disk. Venus orbits the Sun at an average distance of about 0.72 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers. So Venus is about 30% closer to the Sun than we are. At that distance, it receives approximately 1.9 times as much solar energy as the Earth does. Nearly twice as much light, nearly twice as much warmth, pouring down from the sun that appears slightly larger in the Venusian sky than it does in ours, from the surface of Venus. If you could stand there, which you cannot, for reasons we will come to in later chapters, the sun would look like a somewhat brighter, somewhat more intense star, hanging in an amber sky, not dramatically larger, but perceptibly so, wider, more present. Venus completes its orbit of the sun in about 225 Earth days. Its year, by our measure, is roughly 2/3 the length of ours. If you lived on Venus, you would celebrate your birthday considerably more often than you do here. But here's the thing about Venus and time that is genuinely, quietly strange. While Venus moves quickly around the sun, completing its year in 225 days, it rotates extraordinarily slowly on its own axis. One full rotation of Venus takes 243 Earth days. Take a moment to let that settle. Its year, the time it takes to go all the way around the sun, is shorter than its day, the time it takes to spin once on its axis. On Venus, one day is longer than 1 year. You could, in theory, celebrate the new year twice before the sun had completed a single journey across the Venusian sky. The year would turn over, and then turn over again, and still that slow, burning sunrise would not quite have reached its noon. There is something almost dreamlike about this inversion of ordinary time. The fundamental rhythms we take for granted, the year longer than the day, the planet spinning many times for every single orbit, simply do not apply to Venus. It operates by its own clock, ancient and slow and entirely indifferent to our expectations. And there's another strangeness to Venus's rotation, one that gives a quality unlike almost any other world in the solar system. It spins backwards. If you could look down at our solar system from above the sun's north pole, you would see most planets rotating in the same direction, anti-clockwise, the same direction they orbit the sun. This is a remnant of the original spinning disk of gas and dust from which the solar system formed. Everything inherited the same spin from the same source. But Venus turns the other way, slowly, majestically, in the opposite direction to its orbit, to Earth's rotation, to the general agreement of the solar system. This is called retrograde rotation. What this means in practice is that if you stood on Venus and watched the sky, through whatever miraculous protection you had arranged against the heat and the acid, you would see the sun rise in the west and set in the east, the opposite of everything you have ever known. Why Venus rotates this way is still not entirely settled. Perhaps it was struck early in its history by a large impacting body that tipped it over. Perhaps complex atmospheric tides slowed its rotation over billions of years and eventually reversed it. Perhaps it has always been this way, a small original tilt amplified into a full inversion over geological time. We do not know for certain. Venus keeps its own counsel, and yet, for all its strangeness, there is a precision to Venus's movements that is almost mathematical. The orbital resonance between Venus and Earth, the way their two paths around the sun interact over time, produces something remarkable. Over every 8 Earth years, Venus completes almost exactly 13 orbits. 8 and 13. Two numbers close together in a particular mathematical sequence you may have encountered. And this near-perfect ratio means that every 8 years, Venus and Earth return to almost exactly the same relative positions. But there is something even more lovely hidden inside this relationship. If you were to plot the points of each inferior conjunction, each time Venus passes between the Earth and the Sun, over a period of 8 years, and then connect those points in sequence, you would trace a 5-pointed star, a pentagram, not drawn by any human hand, but written into the geometry of 2 planets orbiting a star, emerging naturally from the mathematics of motion. The ancients did not know this explicitly, in the way we can now calculate with precision, but they observed its consequences, the 5 returns, the 8 years, the regularity and beauty of the cycle, and felt perhaps that there was something meaningful in the pattern, something intentional. It was not intentional in any human sense. It was simply mathematics doing what mathematics does, producing from simple rules applied patiently over long stretches of time, patterns that take the breath away. The solar system drawing pentagrams in the sky, and Venus with its backward spin and its years shorter than its day and its reflective clouds and its ancient mythological names, tracing that slow, perfect star above our heads, patient, precise, utterly indifferent to whether anyone is watching. The night is deeper now than it was when we began. You have traveled, without moving, across centuries of human watching. You stood alongside Babylonian astronomers in their towers, recording the light of Ishtar on clay tablets that would survive 4,000 years. You have sat with Mayan scholars in the cool before dawn, watching the eastern horizon for the precise moment of Venus's reappearance, recording it in a book that would be preserved across centuries and consulted by astronomers today. You have looked through Galileo's small, imperfect lens and seen a crescent where there should not have been a crescent, and felt the world rearrange itself around a new geometry. And you have glimpsed, perhaps, that strange inversion at the heart of Venus, a day longer than its year, a sun rising in the west, a world that does not keep the same time as the rest of us. Let your own time soften now. The hours of the night are generous. You do not need to account for them. Let them pass slowly, the way Venus passes slowly across the face of the sun, unhurried, deliberate, leaving a faint trace of wonder in its wake. There is more to come, many more quiet facts, many more gentle wonders, waiting for you in the dark. But for now, simply rest. Breathe. The night is yours. Imagine a day that lasts 4 months. Not a long day in the way we sometimes use the phrase. A difficult day, an exhausting day, a day that seems to stretch, an actual day, a rotation. The sun climbing from its horizon to its noon, and then descending to its opposite horizon, all of it happening over the course of 117 Earth days. That is a Venusian solar day, because of the way Venus rotates, slowly, backwards, tilted almost perfectly upright. The sun moves across its sky with extraordinary deliberateness. It takes 58.5 Earth days to travel from the eastern horizon to its highest point in the sky, then another 58.5 Earth days to descend to the western horizon, and then, of course, an equal span of darkness on the other side, before the whole slow procession begins again. 117 days of light, 117 days of dark. If you were a creature evolved for that rhythm, if your biology ran not on 24 hours, but on something closer to the orbital period of Earth around the Sun, you might find it perfectly natural. But from our perspective, it is almost incomprehensible. The concept of waiting for noon, of a sunrise that began nearly 2 months ago and has only now reached the top of the sky. There is something almost hypnotic about imagining it. The sun barely moving, the shadows changing almost imperceptibly, time stretched out to dimensions our bodies cannot feel. We have already touched on the backward spin, the retrograde rotation that means the sun rises in the west and sets in the east on Venus. But it is worth sitting with this image a little longer, because it is genuinely one of the strangest things in the solar system. Everything in our ordinary experience of the sky proceeds in one direction. The sun rises in the east. Stars wheel from east to west. The moon moves across the sky in the direction we expect. These patterns are so deep in human experience that they are almost unconscious. We navigate by them. We structure our time by them. We have built entire mythologies around them. On Venus, all of that is reversed. The sun rises in the west, not by a small amount, not a quirk that would only matter to a precise astronomer, but completely, literally, the opposite direction. The first light of Venusian dawn comes from the west, slowly brightens over the course of many Earth days, and the sun eventually sets, long afterward, in the east. Why did Venus end up this way? Astronomers still debate the precise cause. One possibility is that early in the solar system's history, when worlds were still forming and the space between them was crowded with debris and collisions, Venus was struck by something large enough to knock its spin into reverse. A world-sized impact, slow and enormous, tipping the planet's rotation over billions of years into the orientation we observe today. Another possibility is more subtle and more interesting. Venus's thick, massive atmosphere, which we will explore in more detail as the night goes on, generates powerful tidal forces on the planet's solid body. The atmosphere slows the rotation, adds its own angular momentum, and through a complex feedback over geological time, may have nudged and eventually reversed the spin. Not a single catastrophic collision, but a slow, relentless atmospheric pressure, working across billions of years, gently reversing the rotation of a world. And there's evidence, quiet, careful astronomical evidence, that this process has not stopped. Some studies suggest that Venus's rotation rate may be changing slightly even now, decade by decade, as atmospheric torques continue their patient work. The planet is still being pushed, still very slowly, being reshaped by its own air, Venus has almost no axial tilt. Earth leans at 23.5 degrees relative to its orbital plane, and that lean is the reason we have seasons. When the northern hemisphere is tilted toward the sun, we receive more light, more warmth, longer days. When it tilts away, we receive less, shorter days, colder air, the long slant of a winter sun. Venus tilts at just 3 degrees, almost perfectly upright, almost precisely perpendicular to its orbital path. And because of this, the sun rises and sets to nearly the same height in the sky every Venusian day, and the poles receive nearly as much light as the equator, and no part of the planet tilts meaningfully toward or away from the sun as the year progresses. No seasons. On Venus, there is no autumn, no slow shift in the quality of light in the late afternoon, no spring, no particular morning when the air smells different and something in the world has changed. Just the same slow burning, overcast day, repeating with almost perfect consistency, year after year, across billions of years. It is a world without change of the kind we find beautiful, without the rhythmic turnover of the seasons that gives our year its shape and meaning. But there is something peaceful in the thought of it too, if you allow it. A world so stable, so consistent, so removed from the ordinary drama of tilting and warming and cooling. A world that simply is, identically, from one long slow day to the next, and yet for all its alien strangeness, Venus is our nearest sibling in the solar system. It is classified as a terrestrial planet, one of the 4 rocky worlds of the inner solar system, alongside Mercury, Earth, and Mars, not a gas giant like Jupiter or Saturn, inflated to hundreds of times our size by vast clouds of hydrogen, not an ice giant, remote and frigid like Uranus or Neptune. A solid planet with a proper surface, composed of rock and metal, beneath a proper atmosphere. In that sense, Venus is recognizable. It belongs to the same family as our own world. It was made of the same raw materials, in the same neighborhood, at roughly the same time. And when you look at the numbers, the resemblance becomes almost uncomfortable. Venus has a mass of approximately 81% of Earth's. Its diameter is roughly 12,100 kilometers, about 5% smaller than Earth's 12,700. Its density is 5.24 grams per cubic centimeter, compared to Earth's 5.51. Nearly identical. These are not small similarities. These are the closest pair of planets in the solar system by size and mass. If you were to hold a scale model of Venus beside a scale model of Earth, you would need to measure them carefully to be certain which was which. The same bulk, the same rocky bones, probably the same general layered structure, an iron core at the center, a mantle of silicate rock surrounding it, a thin crust on top. The same density hints at the same proportions of iron and rock, the same kind of interior, the same origin story. For a long time, in the early days of planetary science, astronomers imagined that Venus might be something like a tropical Earth, covered in clouds, yes, but perhaps warm oceans beneath them, perhaps dense vegetation, perhaps life. The clouds were so thick that no one could see through them, and it was almost irresistible to fill that mystery with hope. The reality, when spacecraft finally penetrated those clouds and reached the surface, was something else entirely. But we will come to that slowly, gently over the hours ahead. For now, hold the simpler image. Two worlds formed from the same cosmic dust, orbiting the same star, almost identical in size and weight, born together, shaped together, made of the same fundamental materials. There's something charming about this, not foolish. The planet really is startlingly, disarmingly bright, especially on a humid or hazy night when it floats low in the sky and seems to pulse slightly as its light filters through moving air. It does look, in certain conditions, almost impossibly brilliant, almost too bright to simply be a planet. But there it is, patient, unchanging, ancient, the evening star, the morning star, the shepherd star, the star of Ishtar, the light that lit the faces of every human being who has ever stepped outside and looked up at the western horizon as the sky darkened and the first point of light appeared. Venus, the sky above you tonight holds that same light. If you could see through the ceiling, through the walls, that same bright point that is hung above every sleepless person who has ever lived, that same pale gold radiance that the ancient Babylonians recorded on clay and the Mayans calculated across centuries, is up there now, in the dark. You do not need to look for it. It knows where you are. Let your eyes be heavy now. Let your thoughts drift a little further from the day. We have a long, quiet journey still ahead of us. So many more gentle wonders to unfold. But there is no hurry. We are traveling at the speed of Venus, slow and luminous, steady and ancient. Let your breathing slow. Let your body sink a little deeper. Long before anyone knew what Venus was made of, long before anyone could calculate its distance or guess at its temperature or imagine anything about its surface, people knew its rhythm. They knew it the way you know the rhythm of a familiar piece of music, even when you cannot name the notes. They knew it because they had been watching and recording and watching again, generation after generation, passing the knowledge between them like a flame cupped against the wind. The Babylonians were among the most careful. To the astronomers of ancient Babylon, Venus was Ishtar, the great goddess of love and war, of desire and destruction. She was not simply beautiful. She was powerful, and her movements in the sky were not decorative but significant, carrying meaning about what was to come, about harvests and battles, about kings and seasons. The Babylonians tracked Venus across a cycle of approximately 8 years. They observed that after 8 years, the planet returned to very nearly the same place in the sky, at the same time of year, appearing at the same point on the horizon at the same time of morning or evening. It was close enough that they could align their temple rituals to it, organizing their religious calendar around the planet's slow, reliable return. 8 years between repetitions. And in those 8 years, Venus would complete exactly 5 of its characteristic cycles, 5 disappearances and reappearances, 5 transitions from evening star to morning star and back again. The number 5, the number 8, 2 numbers that would come to mean Venus across the ancient world in ways that were not entirely coincidental. Far across the ocean, in the rainforests and highlands of Mesoamerica, the ancient Maya arrived at something similar through entirely independent observation across many centuries. With remarkable precision, the Maya calculated the synodic period of Venus, the time it takes for the planet to return to the same position relative to the Sun as seen from Earth, as 584 days. The actual value is 583.92 days. They were off by less than a day, without telescopes, without computers, without any instrument more sophisticated than a straight stick driven into ground to cast a shadow, and a patient pair of eyes, and a system for recording what those eyes saw. The Maya built this knowledge into their sacred calendar. The 365-day solar year and the 584-day Venus cycle produce a combined repeating period of exactly 2,920 days, or 8 solar years or 5 Venus cycles. And they use this alignment, this slow interlocking of cycles, to determine the timing of important events, including, apparently, the timing of warfare. Certain Venus apparitions were considered auspicious for launching campaigns. There is something almost meditative about the patience this required. Generations of astronomers sitting with their observations, not rushing conclusions, letting the pattern reveal itself over years and decades, trusting that if they simply kept watching, the truth would eventually emerge. A slow science, practiced quietly in the dark. In 1610, a man in Padua pointed a small, imperfect telescope at Venus for the first time. His name was Galileo Galilei, and what he saw changed the way human beings understood their place in the solar system. He saw that Venus had phases, like the moon, which grows from a thin crescent to a full circle and back again as it moves through its orbit. Venus, when observed through even the simplest optical instrument, showed the same progression: a thin sliver of light, then a half disk, then a nearly full globe, then shrinking back again. This is not simply the heat of being closer to the sun Mercury. The innermost planet, the world closest to the sun of all, is actually cooler on its surface than Venus. Mercury gets scorchingly hot on its day side, reaching temperatures of 430 degrees Celsius, but its nights are bitterly cold, plunging to minus 180. Mercury has no significant atmosphere to hold warmth in. Whatever the sun gives to the day side, the night gives back to space. Venus is different. Venus has an atmosphere so thick, so dense, so saturated with carbon dioxide and other greenhouse gases, that the heat it receives from the sun cannot escape. It enters, it warms the surface, and then the thick blanket of atmosphere above traps it, holds it, builds it up, year after year, across billions of years. The temperature rising, the greenhouse effect feeding itself, the surface becoming hotter and hotter with no mechanism for release. This is called a runaway greenhouse effect, and Venus is the most extreme example of it in the solar system. The result is a surface temperature that barely varies, not between seasons, because Venus has no seasons, but also not between day and night. Because the atmosphere is so thick and so effective at holding heat, the night side of Venus is almost exactly as hot as the day side, not slightly cooler, not even noticeably cooler, almost exactly the same. 475 degrees. On the side facing the sun, on the side facing away from it, at the equator, at the poles, everywhere, always, consistently, mercilessly, without variation. The atmosphere of Venus is composed of approximately 96% carbon dioxide. The remaining 4% is mostly nitrogen, with small amounts of sulfur dioxide and trace quantities of other gases. But the composition alone does not convey the full strangeness of standing beneath that sky. The surface pressure on Venus is 92 times the atmospheric pressure at sea level on Earth. To experience that kind of pressure on our own planet, you would need to dive approximately 3 kilometers beneath the surface of the ocean. The weight of all that water above you, more than 3,000 meters of it, pressing down with the same force that Venus's atmosphere exerts simply by existing. A human body, unprotected, would not be crushed instantly on the surface of Venus, but it would not last long. The pressure would be the least of the problems. In truth, the heat would overwhelm everything else far sooner. For spacecraft, the challenges are extraordinary. The Soviet Venera probes, which managed to land on Venus between the 1970s and 1980s, were the only human-made objects ever to survive on the surface. They were built like pressure vessels, thick walls of metal designed to withstand enormous compression, and they operated, gathered data, and transmitted their findings back to Earth for less than 2 hours each before the heat and pressure overcame them. The longest surviving Venera probe lasted 110 minutes on the surface of Venus. 110 minutes of operation in a place where lead flows as a liquid and the air itself weighs as much as deep ocean water. The data they returned was extraordinary. Surface images, temperature readings, pressure measurements, chemical analyses of the rocks, all of it gathered in those brief, precious minutes before machines fell silent. There is something almost eerie about the density of Venus's lower atmosphere. So thick is the air near the surface that it behaves less like a gas and more like a fluid. Probes descending through experience aerodynamic braking. The kind of resistance you feel when you move your hand through water, an altitude where Earth's atmosphere would offer almost no resistance at all. This is why Soviet mission designers were able to discard the parachutes on their descent probes relatively early in the descent. At higher altitudes, parachutes slow the probe and protect it from the heat of entry. But lower down, in that dense Venusian air, the atmosphere itself does the slowing. The probe falls through something that is not quite air in any familiar sense, something almost viscous, and arrives at the surface moving slowly enough to survive impact. The air is thick enough to catch you, just not kind enough to keep you. High above this crushing, burning surface, something extraordinary happens. The upper atmosphere of Venus moves at a completely different speed from the planet beneath it, while the surface of Venus rotates once every 243 Earth days. That slow, backwards, stately revolution. The clouds above it circle the planet once every 4 Earth days. The upper atmosphere completes its full rotation 60 times faster than the surface below. This phenomenon is called atmospheric superrotation, and it is one of the most dramatic examples of its kind in the solar system. The winds at the cloud tops reach speeds of over 350 kilometers per hour, faster than the most powerful hurricanes on Earth, and they circle the planet continuously, driven by a mechanism that planetary scientists are still working to fully understand. It is as though the sky and the ground have entirely decoupled from one another, as though Venus has 2 rotation rates, one for its solid body, slow and stubborn and backwards, and one for its atmosphere, racing ahead, indifferent to the lumbering world beneath it. Imagine looking down from the cloud tops. If you could, watching the surface below turn its slow retrograde revolution, one complete turn every 8 months, while you yourself circle the planet in 4 days, lapping the surface again and again, outpacing the solid world by a factor of 60. The atmosphere of Venus does not wait for the ground. It has its own agenda, its own momentum, its own furious and ancient energy. The world below those clouds is still. The world above them races. And somewhere between them, in the thick amber murk of the middle atmosphere, there's a zone, and we will come to this in hours ahead, that is almost temperate, almost, in some ways, almost familiar, but that is a thought for later when the night is deeper. For now, let the strangeness of Venus simply wash over you. A world without moons, without seasons, without the small mercies of temperature variation. A world where gravity would feel almost like home, right until everything else did not. Let the weight of it go. Let the pressure of your own day release. All of it quietly into the dark. You are here, warm and safe, in a world with a reasonable atmosphere and a sensible temperature, and a moon that rises and falls above you on its own quiet schedule. Rest now. We have many more hours of soft wonder still to come. The atmosphere of Venus is a place of extremes layered within extremes. From the crushing, still heat of the surface to the racing clouds far above, and then beyond those clouds, higher still, into realms of cold and ice that seem impossible on the hottest planet in the solar system. There's an entire vertical world of weather happening above Venus, a world of weather that had been working without pause for billions of years. Let us ascend through it together, slowly, one layer at a time. We have already spoken of the cloud tops, where the atmosphere races around the planet once every 4 Earth days. Winds of over 360 kilometers per hour, circling endlessly, indifferent to the slow rotation of the surface far below. Winds powerful enough to outpace a commercial aircraft. Winds that have been blowing, without interruption, for geological ages. These cloud-top winds are driven by energy. The sun pours its radiation down onto Venus's upper atmosphere, and that energy has to go somewhere. It cannot easily reach the surface. The atmosphere is too opaque, too dense, too layered with cloud and haze. So the energy stays near the top, warming the cloud layers, driving the circulation, maintaining that relentless supersonic spin. From above, the cloud tops of Venus would look almost beautiful. Endless swirling patterns, vast rolling spirals, lit in shades of pale gold and cream by the sun, in ultraviolet light, where certain atmospheric chemicals absorb strongly, the patterns become even more dramatic. High contrast swirls of dark and bright, the Terminator. The line between the day and night sides, sharp and clear as a knife edge, because the dense clouds create a hard boundary between illuminated and dark. A world of cloud viewed from space, endlessly moving, endlessly rearranging, never the same from one Venusian day to the next, even as the surface below remains locked in its unchanging heat. But descend now, through those clouds toward the surface. Something strange happens as you drop lower. The winds begin to slow. The roaring, racing atmosphere of the cloud tops gives way, gradually, to something much more sluggish. At the surface itself, the winds move at just 1 to 2 miles per hour, a gentle breeze by any measure, the kind of wind that would barely stir a candle flame. And yet, even at 1 to 2 miles per hour, the surface winds of Venus carry force. Because the air is so dense, 92 times denser than our own, even a slow wind carries an extraordinary amount of momentum. On Earth, a gentle 2-mile-per-hour breeze is imperceptible. On Venus, the same wind speed creates enough force to move small rocks. Geologists studying the surface have found evidence of rock formations and dust patterns consistent with slow but persistent wind erosion. The landscape shaped not by howling storms, but by the patient, heavy breath of an enormous atmosphere, pressing and moving at walking pace, year after year, across millions of years. Weight doing what speed cannot, the slow force of accumulated pressure, moving the world grain by grain. High above the surface, at the poles of Venus, the atmosphere does something remarkable. At each pole, a persistent polar vortex is formed, a vast, swirling structure of cloud and wind, centered on the planet's axis of rotation. Earth has polar vortices too, and they influence our weather in ways that occasionally make headlines. But Venus's polar vortices are different. They are double-eyed. Where Earth's polar vortex has a single center rotation, Venus's polar vortices appear to have 2 distinct eyes, 2 spiraling centers, rotating around each other in a slow gravitational waltz. The overall structure extends for thousands of kilometers. It has been there for as long as we have been able to observe it. It may have been there for millions of years. Imagine the scale of it. A spinning structure cloud large enough to swallow a continent. Circling slowly above the pole, 2 eyes of calm within it. Seen from above in infrared, It glows with the trapped warmth of the planet beneath it. A dark, slow, enormous pinwheel suspended above the hottest world in the solar system. There is something both unsettling and beautiful about it, viewed from a sufficient distance. The kind of thing that reminds you, gently, that the solar system is full of structures we have barely begun to understand. And somewhere in those layered, churning clouds, it rains. The clouds of Venus are composed largely of sulfuric acid droplets, extraordinarily corrosive, extraordinarily dense. And from those clouds, droplets fall, acid rain, descending toward the surface of Venus. But here's the thing. The rain never arrives. The surface of Venus is so hot, 475 degrees Celsius, that the sulfuric acid droplets evaporate long before they reach the ground, somewhere between the cloud layer and the surface, at altitudes of perhaps 25 kilometers or so. The falling droplets meet air hot enough to vaporize them. They dissipate back into the atmosphere, rising again, reforming into clouds, falling again, evaporating again, an endless cycle of rain that never lands. Acid falling through amber sky toward a surface it can never touch, pulled apart by heat before it reaches the ground, rising again on thermals, rejoining the clouds it came from. There's something almost meditative about this image. The rain falling and evaporating and reforming in an eternal loop, driven by heat and gravity and chemistry, cycling through the same process across billions of years, going nowhere, arriving nowhere, simply moving in the same slow circle forever, within those same sulfuric acid clouds, in the dense and turbulent layers between 40 and 60 kilometers above the surface. Something else happens. Lightning. Venus has lightning storms. Not a speculation. Actual detected electrical discharges, identified by spacecraft passing close enough to measure the electromagnetic signals. The Venera probes detected them. The European Venus Express mission confirmed them. The lightning on Venus is likely generated by convection, updrafts of hot gas rising to cloud layers, carrying electrical charge, building up differentials until the charge discharges in a flash. A flash of lightning, illuminating briefly the yellow-gray interior of a sulfuric acid cloud, 50 kilometers above the hottest surface in the solar system, completely unseen from the ground, because no light can penetrate the atmosphere to the surface or escape from there to space. A lightning storm in a room with no windows, in a building no one can enter. The universe contains so many things happening in places we cannot go. Above the clouds, the atmosphere continues upward through layers of haze, sulfur particles extending to around 90 kilometers altitude, fed by photochemical reactions in which sunlight breaks down sulfur dioxide and reassembles it into fine particles that drift and settle and drift again. A permanent haze layer, thin but extensive, filtering the light still further, adding another veil to an already veiled world. At 65 kilometers altitude, something unexpected happens to the temperature. On Earth, the atmosphere cools as you go higher. This is why mountain peaks are cold. why the upper atmosphere is freezing. Temperature decreases with altitude. This is called the lapse rate, and it is one of the fundamental rules of how atmospheres work. But at 65 kilometers on Venus, the temperature stops falling and begins to rise. This is the tropopause, the boundary layer, where the normal rules are inverted. The carbon dioxide atmosphere, absorbing radiation from both above and below, creates a zone where higher altitude means warmer, not colder. The atmosphere turns itself inside out, thermally speaking, at 65 kilometers. Above this inversion, temperatures rise with altitude for a while before eventually falling again in the very highest layers. And in those very highest layers, on the night side of Venus, something almost impossible happens. The upper atmosphere on the night side of Venus, the side facing away from the sun, cools to extraordinary temperatures, minus 170 degrees Celsius, minus 274 degrees Fahrenheit, on the hottest planet in the solar system, in the upper atmosphere. On the dark side, at those temperatures, exotic ice clouds can form, not water ice, but ice made of hydrogen-bearing compounds, forming an atmosphere that is otherwise an inferno. Thin, cold, improbable clouds drifting in the upper darkness of a planet that, 60 kilometers below them, is dissolving lead. The universe does not keep its extremes separate. It layers them, stacks them on top of each other, surprises you with cold at the heart of heat and stillness at the center of a storm. And threading through all of this, through the sulfuric rain and the lightning and the polar vortices and the racing cloud tops, are trace gases, small amounts of nitrogen, carbon monoxide, argon. These tiny constituents are more than impurities. They are clues. The ratio of different argon isotopes in Venus's atmosphere tells us about the early bombardment history of the solar system, about how much material was delivered to Venus by asteroids and comets in the first billion years after formation. The presence of carbon monoxide tells us about ongoing chemical cycling in the lower atmosphere. The nitrogen content gives us hints about how the atmosphere evolved over geological time. These trace gases are the fingerprints of Venus's history. The chemical record of 4.5 billion years of planetary life, volcanic outgassing, asteroid impacts, atmospheric evolution, the slow transformation of a world, every molecule a memory. The atmosphere of Venus is a place of extraordinary complexity. Wind and acid and lightning and ice, all layered on top of each other, all happening simultaneously, all powered by a sun that Venus has been orbiting for longer than life has existed on Earth. We, from here, cannot see any of it directly. The clouds hide everything. The planet shines above us smooth and brilliant and impenetrable, a polished ball of light that gives nothing away. But we know it is happening right now, as you lie here, as your breathing slows and your thoughts begin to loosen their grip. High above you, a world is in constant motion, acid falling and evaporating, lightning flashing in amber cloud, polar vortices turning their slow double spiral above the poles of the moonless, seasonless, backward spinning world. None of it touching you, none of it requiring anything of you, simply happening as it has happened for billions of years, as it will happen for billions more. You are very still. And somewhere up there, Venus is very busy. Let your stillness deepen. Let the night do its quiet work. There is water on Venus, almost no water. A trace so faint it is measured not in percentages, but in parts per million, but water nonetheless, lingering in the atmosphere, a ghost of something much larger. The water vapor in Venus's atmosphere today accounts for roughly 0.002% of what is present. It cycles through the planet on a very long, slow path. Volcanic activity releases it from the interior. Chemical reactions in the atmosphere bind it back into minerals and sulfates. A quiet, geological water cycle, utterly unlike the generous cycle of evaporation and rain and rivers that shapes our own world, but cycle nonetheless, enduring at the margins. This trace of water matters enormously to the question of what Venus once was, because models of early planetary formation suggest that Venus, in the first billion years or so of the solar system's history, may have had liquid water on its surface. Real water. Oceans, perhaps shallow, perhaps deep, sheets of liquid covering its volcanic plains, reflecting the younger, somewhat dimmer Sunday. An atmosphere different from the one that exists today. Thinner, cooler, less smothering. Of Venus that, at least briefly, may have been habitable. This is not a small hypothesis. It is supported by the chemistry of what we find in Venus's atmosphere today. The ratios of certain isotopes, the abundance of certain gases, that suggest the planet once held much more water than it does now. The water is gone, but the evidence of its departure remains, written in the molecules that stay behind. What happened to it? As the sun gradually brightened over geological time, as it does, slowly and inevitably, all stars growing slightly hotter as they age, Venus received more and more solar energy. The oceans began to warm. As they warmed, more water evaporated into the atmosphere. As more water entered the atmosphere, the greenhouse effect strengthened. As the greenhouse effect strengthened, the planet warmed further, which evaporated more water, which strengthened the greenhouse effect further. A runaway feedback. A positive spiral with no natural stopping point. The oceans boiled. The water vapor rose high into the atmosphere. Where ultraviolet radiation from the sun broke the water molecules apart, splitting hydrogen from oxygen. The hydrogen, light enough, escaped to space. The oxygen combined with surface rocks and volcanic gases, and the water, drop by drop and molecule by molecule, vanished from Venus over hundreds of millions of years. What had been, perhaps, a gentle shallow ocean became first a desert, then an inferno. The seas of Venus are in space now, scattered as individual hydrogen atoms, carried away by the solar wind across billions of years, dispersed among the stars. And yet the atmosphere of Venus is not finished being mysterious. In the cloud layers, at altitudes of around 50 to 60 kilometers, something is absorbing ultraviolet light. This is not controversial. Spacecraft and telescopes have observed it clearly, but what is absorbing the ultraviolet is still not known. These unknown absorbers give Venus's upper clouds a distinctive banded appearance when viewed in ultraviolet, streaks and patches of dark material, shifting and reforming as the clouds circulate, absorbing UV efficiently in a way that is difficult to explain with known chemistry alone. Several explanations have been proposed. Certain sulfur compounds could do it. Iron chloride particles have been suggested. Photochemical reactions in the unusual atmospheric chemistry of Venus might produce exotic molecules capable of absorbing at these wavelengths. And then there's the other possibility, which one cannot entirely dismiss without investigation. Life. Some microorganisms on Earth absorb ultraviolet light as a byproduct of their metabolic processes. Certain sulfur-based bacteria, which can tolerate acidic conditions that would kill most living things, are among them. The cloud layers of Venus, at altitudes of 50 to 60 kilometers, are among the least hostile environments in the solar system outside of Earth itself. Temperatures in a range of 20 to 60 degrees Celsius, pressures comparable to the surface of Earth, and abundant sulfur compounds as a potential energy source. These clouds are, in a narrow technical sense, within the range of conditions that some Earth life can tolerate. Not comfortably, not easily, but within the range. In 2020, a team of astronomers announced that they had detected phosphine gas in the atmosphere of Venus. Phosphine, a molecule of one phosphorus atom and 3 hydrogen atoms, is, on Earth, predominantly produced by biological processes, microbes in oxygen-poor environments, decaying organic matter. It is not produced in meaningful quantities by any known non-biological, geological, or chemical process in the conditions found in Venus's atmosphere. The announcement was cautious and careful. The researchers were not claiming to have found life. They were noting an anomaly, a chemical that should not, according to our current understanding, be present in the Venusian clouds, and yet appear to be there. The scientific community responded with intense scrutiny, as it should. Subsequent analyses questioned the original data. The signal, it was argued, may have been weaker than originally reported. Instrumental artifacts may have contributed. Alternative explanations, exotic photochemistry, perhaps volcanic sources not yet characterized, were proposed and debated. The question is not settled. The data remain disputed. The search continues. But the episode opened something, a door, slightly ajar, into a possibility that seemed remote, that somewhere in the thick, acid-laced clouds of our nearest planetary neighbor, something might be alive. Not complex life, not intelligent life, but chemistry doing something that we associate on our own world with the presence of organisms, a microbial biosphere drifting in the amber clouds of Venus. surviving in conditions that would kill any animal, any plant, most fungi. But alive, we do not know. We may not know for a long time, but we are asking the question, below all of this, below the clouds and the haze and the acid rain and the lightning and the ultraviolet absorbers and the trace of phosphine, lies the surface of Venus. And the surface tells its own long, slow story. More than 90% of Venus's surface is covered by volcanic plains. Flat, wide expanses of solidified lava, reshaped relatively recently in geological terms, within the last 500 million years or so, by enormous floods of volcanic material. The surface we see today is not the surface that existed when the solar system was young. It was remade, paved over, resurfaced, buried under waves of lava that cover the older landscape almost completely. This is why Venus has so few impact craters. The moon, with its ancient unchanged surface, is pockmarked with craters from billions of years of bombardment. The record of every impact preserved in the lifeless rock. Venus has far fewer craters, and they are distributed relatively evenly across the surface, suggesting that the entire surface was renewed at roughly the same time. Something happened on Venus 500 million years ago that reshaped the entire planet. A global volcanic event. Not a slow, ongoing process, but something more dramatic. A pulse of enormous volcanic activity that flooded the surface with lava on a scale almost impossible to conceive, covering everything that had existed before with new rock. What triggered it? The slow buildup of heat within the planet, which cannot escape to the kind of plate tectonic recycling that cools the Earth's interior. Instead, the heat accumulates, pressure builds until the crust cracks and the interior erupts, not locally, not in one range of volcanoes, but globally. A planet-wide resurfacing. An entire world remade in lava. Venus has no magnetic field of its own, not a significant one. Unlike Earth, which has a rotating iron core generating a protective magnetic field that deflects most of the solar wind, Venus's core appears to generate no such protection. And so the solar wind, the constant stream of charged particles flowing outward from the sun, meets Venus's atmosphere directly, without a magnetic field to deflect it. The solar wind interacts with the ionosphere, creating what is called an induced magnetosphere. The atmosphere itself develops a kind of bow shock, where the solar particles pile up against the leading edge of the planet, and a long magnetotail, like the tail of a comet, streams out behind Venus in the direction away from the sun. Venus, in effect, pretends to have a magnetic field, not through its core, but through its atmosphere. The ionosphere stands in for the magnetosphere, doing an imperfect job of protecting the planet's upper air from solar erosion, but doing it nonetheless. This ionosphere peaks at around 140 kilometers altitude, ionized by extreme ultraviolet radiation from the sun. It is both the planet's shield and its vulnerability, the only barrier between Venus's atmosphere and the stripping force of the solar wind. Without a real magnetic field, without the protection that Earth takes for granted, Venus loses a little of itself to space, particle by particle, every single day. There is buried in all of this something quietly humbling. Venus and Earth are so similar in their raw ingredients. The same size, the same mass, the same density, probably the same rocky iron composition. They form at the same time from the same solar nebula. They were given at the beginning roughly the same possibilities. And somewhere in the first billion years, the paths diverged. Venus lost its water, possibly lost its tectonic activity, lost its magnetic field, locked its own atmosphere against it. And the result of all those small divergences, each one individually perhaps not dramatic, each one a small difference from what Earth did, is a surface temperature that melts lead, a pressure that crushes spacecraft, and a sky full of acid, all of it from the same starting materials as home. The night is deep now. You have been lying here long enough that the day feels very far away. The concerns of the morning are smaller than they were. The thoughts that come and go are slower, softer, less insistent. Somewhere above the cloud tops of Venus, in the thin, cold reaches of the upper atmosphere, something may be drifting, a trace of chemistry that does not quite make sense, a molecule that should not be there. We do not know what it is. We may not know for decades. And there's something strangely peaceful about that not knowing, about a question that will remain open, hanging in the amber clouds of another world, while we rest here in the safe dark of this one. Let the unanswered question drift. Let the mystery of Venus do what good mysteries do, not agitate, but simply float quietly in the back of the mind. You are nearly asleep. The world is very still. Consider what it takes to reach the surface of Venus. A meteoroid hurtling through space, a fragment of rock or metal, perhaps the size of a house, perhaps the size of a small building, enters a Venusian atmosphere, on the moon or on Mars where the air is thin. Such an object would reach the surface with most of its energy intact, carving a crater that records the impact for billions of years. But on Venus, the atmosphere is waiting. The thick, dense 92-atmosphere blanket of carbon dioxide begins its work immediately. The meteoroid decelerates. The air ahead of it compresses into a shock wave of extraordinary pressure. Smaller objects, anything below roughly 3 kilometers in diameter, do not survive the descent. They are shredded, ablated, broken apart, and dispersed into the lower atmosphere as vapor and fine particles before they ever touch the ground. Only the large ones get through. Objects massive enough to punch through 92 atmospheres of resistance survive in the heat of entry, arriving at the surface with enough momentum to excavate a crater. Venus has approximately 900 impact craters. Every single one of them is larger than 3 kilometers across. There are no small craters on Venus, not because small meteoroids never approach the planet, but because none of them are large enough to survive the journey down. It is as though the planet has a minimum entry requirement, a threshold of size and mass below which everything is simply consumed by the sky. Those 900 craters are distributed across Venus's surface with particular quality that tells geologists something important. They are relatively randomly scattered, without the clustering or degradation patterns that would suggest an old, heavily bombarded surface. On the Moon, craters pile on top of craters. Ancient impacts are blurred and eroded by later ones, layered across billions of years of bombardment. The oldest parts of the lunar surface are saturated with overlapping craters, a geological palimpsest of the solar system's violent youth. Venus shows none of this. The craters are relatively fresh, relatively evenly distributed, almost as though they were all made at roughly the same time, or rather, as though the surface they are sitting on was all created at roughly the same time, and the craters accumulated afterward. This is the clearest evidence for what geologists suspect, that Venus's surface was almost entirely remade in a relatively short period, somewhere between 300 and 600 million years ago, a global resurfacing, after which the crater count began again from near zero. Why does this happen? Venus has no plate tectonics. On Earth, the crust is divided into moving plates that carry the continents across the surface, dive back into the mantle at subduction zones, and allow heat from the interior to escape in a steady, managed way. This process is an efficient heat pump, keeping the Earth's interior from overheating. Venus has no such mechanism. Its crust is a single unbroken shell, thicker in some places, thinner in others, but not divided, not moving, not cycling. And so the heat trapped in Venus's interior has no regular outlet. It accumulates slowly, over hundreds of millions of years, building and building beneath that immovable lid, until it can no longer be contained. At some point, perhaps every 300 to 600 million years, the pressure reaches a threshold. The crust cracks, not in one place, but in many. Lava floods out across the surface in volumes almost beyond imagination, repaving the planet. The old landscape, wherever it was, disappears beneath wave after wave of basaltic lava, flowing for hundreds of kilometers across the plains, filling in valleys and plains and hollows. Then the crust seals again. The heat begins to build, and the slow countdown to the next resurfacing begins. Across Venus's plains, the radar instruments of orbiting spacecraft have traced the outlines of vast lava flows. Flows that extend not for kilometers but for hundreds of kilometers. Rivers of molten rock that poured across the surface when Venus's interior was particularly active, cooling slowly in the thick atmosphere, solidify into flat plains that cover more than 90% of the planet today. These flows were almost certainly very fluid. The basaltic lava that erupts from similar volcanoes on Earth flows easily, spreading wide, traveling far before it cools. On Venus, where the surface temperature is already 475 degrees, the lava may have remained fluid even longer, spreading further, covering more ground before it finally solidified. The result is a landscape of remarkable flatness, gently rolling plains of ancient lava, stretching to every horizon, occasionally interrupted by the dramatic exceptions: the highlands, the volcanoes, the rifts. Venus has volcanoes, many volcanoes. More than 1,600 major volcanic features have been cataloged on its surface, along with countless smaller ones. Shield volcanoes rising gently above the plains, steep-sided volcanic domes, calderas, collapsed summits left behind when the magma chamber beneath a volcano empties and the roof caves in. And rising above all of them, in the highland region called Ishtar Terra in the northern hemisphere, is Maxwell Montes. Maxwell Montes is the highest mountain on Venus. Its peak stands approximately 11 kilometers above the average surface elevation, roughly 36,000 feet, taller than Mount Everest measured from sea level. It is a vast radar-bright massif, rising steeply from the high plateau of Ishtar Terra like the spine of a continent. Ishtar Terra itself is approximately the size of Australia, a vast elevated region of ancient, deformed terrain, surrounded by steep scarps and mountain ranges that mark where enormous geological forces have pushed the crust upward. It sits in the northern hemisphere like a cap, its highest peaks gleaming bright in radar images because of the unusual minerals that condense there at altitude, metals that vaporize near the surface and precipitate onto cooler peaks, giving them a metallic sheen. And in the equatorial regions, straddling the planet's middle latitudes, lies Aphrodite Terra, a highland region comparable in size to South America. Aphrodite is more fractured, more complex than Ishtar, cut by vast rift zones and dotted with volcanic features, a region of enormous geological activity that extends across a third of Venus's circumference. Two continents of a kind, not carried on tectonic plates. Venus has no plates, simply raised terrain, pushed up by the forces of the interior over long periods, standing above the lava plains like islands above a frozen sea. Cutting through Venus's landscape are the Casamata, vast rift valleys, some of them thousands of kilometers long, not carved by water, not shaped by the movement of tectonic plates. Instead, they are fractures, places where the crust has been stretched and pulled apart by the forces within, opening into long, deep trenches that run across the landscape. The Artemis Chasma, one of the largest, extends for approximately 2,500 kilometers. Imagine standing at one end of a valley and knowing that it stretches in one direction, farther than the distance from one side of a continent to another, a crack in the world so large that it would take weeks to walk its length. These Casamata resemble, in some ways, the rift valleys of East Africa, the great geological rifts along which Africa is very slowly pulling apart, where new oceanic crust will eventually form over millions of years. But on Venus, without plate tectonics, there is no next stage. The rifts simply exist, open, deep, ancient, with nowhere to go, and flowing across Venus's plains, winding for hundreds and sometimes thousands of kilometers, are what look, at first glance, like river valleys, sinuous channels, branching and meandering, tracing the landscape in long curves. But there is no water on Venus's surface. There never will be again, not at these temperatures. These channels were not carved by liquid water. They were carved by lava. The longest of these lava channels, sometimes called beta valleys or canali in older literature, extends for more than 6,000 kilometers. More than 6,000. That makes it, by some measures, the longest channel of any kind on any solid body in the solar system. A river of lava that once flowed, perhaps continuously for thousands of years, across more than a quarter of the planet's circumference. What kind of volcanic event produces a lava flow 6,000 kilometers long? The lava must have been extraordinarily fluid, erupting in volumes and for durations difficult to conceive, flowing and cooling at the edges, channeling itself into an ever deeper groove, cutting the channel deeper as it went, extending its reach further and further across the plains. Then at some point the eruption ended, the lava cooled, and the channel remained, empty now, ancient, still visible on radar maps made by spacecraft in orbit hundreds of kilometers above. A memory of a river that never held water. The surface of Venus is a landscape of deep time and enormous forces. Mountains that dwarf Everest. Rifts that could swallow entire mountain ranges. Lava flows that stretch across thousands of kilometers. 900 craters, none of them small. And above it all, the thick amber sky, lit from below by the glow of 475 degrees, with no sunlight reaching the ground, with the acid clouds far above and the lightning in the middle layers and the racing winds at the top. It is a world of tremendous scale, a world that does not do anything quietly or human proportions. And from here, from your bed in your room, in the dark and the warmth and the comfortable way of the night, it is simply beautiful to contemplate. A world of extremes, observed from a safe distance. A landscape of volcanic wonder, glimpsed through the instruments of spacecraft that long ago fell silent on a surface that consumed them. All of it very far away, all of it very still. From where you lie, let your thoughts settle into the plains of Venus. Wide, flat, ancient, stretching in every direction to a horizon you cannot quite reach. Let your breathing slow, like lava cooling. Let your eyes be heavy. Venus has invented landforms that do not exist anywhere else. In the Atlas of Planetary Geology, that growing catalog of mountains and craters and valleys and plains that scientists have assembled by sending spacecraft to the worlds of our solar system, certain pages belong only to Venus. Features with names that sound like they came from mythology, from poetry, from the dreams of a planet that has spent 4.5 billion years doing things its own way. Let us spend some time with them here in the deep of the night. There is no hurry. These features have existed for hundreds of millions of years, and they will still be there when morning comes. First, the tesserae. Scattered across Venus's surface are regions of ancient, intensely deformed terrain. The crust here has been folded, fractured, compressed, stretched, and compressed again repeatedly over enormous spans of time until it resembles something like a crumpled piece of geological origami. Ridges up to 3 kilometers high crosshatch the landscape in multiple directions, intersecting at angles that record different episodes of stress, different periods when the forces within the planet were pushing in different directions. Geologists call these regions tesserae, from the Latin word for mosaic tile. The name captures the visual quality, seen on radar maps. The tessera terrain looks like an intricate pattern of interlocking shapes, like ancient mosaic paving laid down by a planet that had too much time and too much internal energy and not quite enough to do with it. These are among the oldest surfaces on Venus. In the sea of relatively young lava plains that covers most of the planet, the tesserae stand as islands of deep time, terrain that, for whatever reason, was not completely buried in the last global resurfacing event, survived, remained, still standing, folded and ancient, rising above the plains that surround them. Nothing quite like them exists on Earth. Then there are the coronae. A corona, singular, is a roughly circular feature, ranging in size from 100 kilometers across to more than 1,000. It is formed when a plume of hot material rises from deep within Venus's mantle, pushing the crust upward into a dome, then sinking back as the plume loses energy, allowing the dome to collapse, leaving behind a characteristic structure of concentric rings, moats, ridges, and fractured terrain, surrounding a central region of volcanic activity. Imagine pressing your thumb gently into soft clay, watching the clay push up around your thumb, and then slowly releasing, watching the clay collapse back but leave a complex ring of ridges around the depression. The coronae of Venus are something like that, but at a scale of hundreds of kilometers and shaped by the movement of molten rock kilometers below the surface. Venus has more than 500 cataloged coronae. They are one of the most distinctive features of the Venusian landscape, and one of the clearest signs of a planet whose interior is active, whose mantle is moving, whose heat is always looking for a way out through an unyielding crust. The novae are different again. Where coronae are circular, novae are radial. They appear as starburst patterns, fractures radiating outward from a central volcanic vent, spreading in all directions like cracks in glass struck at the center or like the petals of an enormous flower. They range from 50 to 200 kilometers across. The name, appropriately, comes from the Latin for new star. Seen on radar, with their radiating pattern of bright fractures, they have a visual quality that is both dramatic and somehow delicate, a kind of geological firework, frozen in time, preserved by the same thick atmosphere that otherwise destroys so much. The novae likely represent an earlier stage of development than coronae. When a mantle plume first rises and pushes against the crust cracks outward in that starburst pattern. If the plume continues, the central dome may eventually form, then collapse, evolving the nova over geological time into a corona. If the plume stops early, the nova stays as it is, a starburst of fractures, a record of a moment when Venus's interior briefly pressed upward against its own skin and was refused entry. And then, most delightful of all, there are the arachnoids. An arachnoid, the name derived from the Greek word for spider, is a feature unique to Venus. It consists of a central volcanic dome or caldera, surrounded first by concentric rings of fractures, and then by a web of radiating lines that spread outward from the central structure like the legs of a spider, or the threads of a web. There are more than 250 confirmed arachnoids on Venus's surface, ranging from roughly 50 to 230 kilometers across. Seen in radar images, they are remarkable, concentric, precise, symmetrical in a way that seems almost intentional, as though the planet were making a pattern. A central dome, rings around it, lines radiating outward. The geometry of a web laid down in fractured rock across a landscape of ancient lava. They are thought to form when magma pushes up beneath the crust, creating the central dome, and the stress of that upward pressure fractures the surrounding crust in the characteristic radial and concentric pattern. The volcanic activity feeds the structure, extending it outward as the magma continues to press. But standing back from a geological mechanism, simply looking at them as shapes, there is something genuinely beautiful about the arachnoids. Spider webs drawn in kilometers of fractured rock. The planet, unknowingly, producing art. Venus also has its pancake domes. These are broad, flat, circular volcanic features, some of them tens of kilometers across, but remarkably thin for their width, with flat tops and steep sides. They look, precisely as the name suggests, like enormous geological pancakes laid on the surface. They are thought to form from very thick, viscous lava, magma so stiff that when it reaches the surface it cannot float easily in all directions. Instead, it pushes up slowly, spreading outward at a similar rate in all directions, forming an even dome. Then it stops, and there it sits, a flat-top mound of solidified viscous rock, perhaps a kilometer thick and 20 kilometers across, surrounded by the level plains. There are more than 100 pancake domes identified on Venus's surface, some clustering groups neighboring each other across the plains. Some stand alone, all of them slightly strange-looking, the product of geology operating in conditions that produce forms we do not see anywhere else. And across the surface, drifting in patterns behind impact craters and volcanic features, are wind streaks, long, dark tails of fine material, swept by the slow surface winds for hundreds of kilometers downwind. They show the direction prevailing surface winds have blown, recorded in dust and fine volcanic particles, marking the landscape with a subtle record of where the air has been. Even at 1 or 2 miles per hour, the wind leaves a trace, a signature in the dust. The atmosphere slowly, patiently inscribing its passage in the landscape it crosses. The rocks themselves are not immune to the atmosphere's chemistry. In the hot, dense, sulfurous air, the surface minerals of Venus react. Iron oxides form. Sulfates accumulate. The rocks develop a weathered coating over time, the chemical product of billions of years of exposure to a sky that would dissolve most metals. We know this not from direct observation, but from the data returned by those brief heroic Venera probes, their cameras showing the surface of dark, angular rocks and pebbles, their chemical sensors detecting the composition, their temperature sensors confirming the extraordinary heat. A landscape that has been chemically active for an unimaginable length of time. Deep beneath that landscape, inside Venus itself, The story continues in the quiet. Venus almost certainly has a layered interior much like Earth's, a solid inner core of iron and nickel at the very center, surrounded by a liquid outer core, surrounded in turn by the mantle of silicate rock, topped by the crust. But there is one critical difference. The liquid outer core of Earth rotates, driven by the Coriolis forces of planet spin, convecting heat outward. And this rotation conducting fluid generates Earth's magnetic field, the dynamo effect, running continuously for billions of years, producing the field that deflects solar wind and protects our atmosphere. Venus rotates too slowly, rotating once every 243 days. The planet simply does not spin fast enough for convection in its liquid core to generate a meaningful dynamo. The Coriolis forces that organize the flow in Earth's core are too weak on Venus to create the ordered circulation that produces a magnetic field. And so Venus has no global magnetic field. Its core spins, the liquid iron churns, but it does not generate the organized current loops that would create a lasting field. The interior of Venus holds its heat, holds its iron, holds all the structural elements of a planet that could have a magnetic field, but cannot quite manage the rotation speed to make it work. A dynamo that will never quite ignite. The deep interior of Venus is dark and hot and very quiet. No seismometers have ever recorded a Venusian earthquake. No probe has ever survived long enough to listen for one. The interior turns in silence, the core conducting its slow, magnetically insufficient rotation, the mantle convecting upward and occasionally cracking the surface in a nova or a corona or a flow of lava across the ancient plains. All of it unseen, all of it inferred from the planet's size and mass and density and the traces it leaves in radar maps and gravitational measurements and the chemistry of its atmosphere. You know very little about what is directly beneath you, right now, beneath the floor and the ground and the rock layers and the crust and the mantle. You know it is there. You infer it from measurements. And Venus is the same, known at its edges, inferred at its heart. Let the mystery of the interior be a restful thing, not an unsettling one, simply a part of the planet's quiet complexity. All that rock and heat and slow motion, happening somewhere deep and dark and removed from everything you need concern yourself with tonight. The surface is still. The arachnoids are still. The pancake domes sit unchanged above their ancient lava fields. And you are very nearly asleep, somewhere in the deep interior of Venus. At the very center, there is a core. Its size is estimated at somewhere between 1/4 and half of the planet's total radius. A ball of iron and nickel, dense and ancient, sitting at the heart of the world the way a seed sits at the center of a fruit. It has been there since Venus formed 4.5 billion years ago. It has never been visited. It has never been directly measured. We know it is the way we know anything about the deep interior of a planet, through inference, through gravity measurements, through the behavior of the planet as a whole. The core is iron and nickel, almost certainly the same materials as Earth's core, dense and hot and very deep and almost certainly partly liquid. the outer layers molten, the innermost region possibly solid, but lacking, as we have already noted, the rotational speed to set that liquid iron spinning in the organized currents that would generate a magnetic field. The energy is there, the material is there, the geometry is almost right, but Venus turns too slowly, and the dynamo does not ignite, and the planet goes unprotected into the solar wind. Surrounding the core, the mantle extends to more than 3,000 kilometers, an enormous thickness of silicate rock, hotter and perhaps stiffer than Earth's mantle, convecting only sluggishly because of the high temperatures and the absence of water, which on Earth plays a surprisingly important role in keeping the mantle pliable and able to flow. On top of the mantle, the crust, relatively thin by the standards of planets with thick continental crust, somewhere between 20 and 50 kilometers on average, thin enough that the forces below can push through it relatively easily, thin enough that when the heat builds up in the mantle, it finds a way out. The crust of Venus contains iron, a great deal of it, proportionally more than Earth's crust. The Venera probes that landed on the surface analyzed the soil around them and found compositions consistent with basaltic rock rich in iron compounds. The same probes returned photographs showing dark, angular rocks of various sizes, partially embedded in fine material, a landscape that, if you could scale it to human proportions and remove the crushing atmosphere and the lethal heat, would perhaps look somewhat familiar, rocky, plain, not so different in the broad strokes from a volcanic field on Earth. The difference, of course, is everything beyond the broad strokes. In 1962, a spacecraft left Earth bound for Venus. It was called Mariner 2, and it was built by NASA, small, angular, bristling with scientific instruments, the product of thousands of hours of careful engineering by people who had never sent a spacecraft to another planet before, because no one had. On December 14th, 1962, Mariner 2 flew past Venus at a distance of approximately 35,000 kilometers. It did not land. It did not orbit. It simply passed, taking measurements as it went, recording Venus's temperature, probing its atmosphere, measuring the solar wind. It was humanity's first visit to another planet. Everything that came after, every probe, every lander, every orbiter, every mission that has expanded our knowledge of the solar system, traces its lineage, in some sense, back to that single quiet flyby, a small machine passing a hot, bright planet. In the December of 1962, the data Mariner 2 returned were surprising. The surface temperature was far higher than many scientists had hoped. The dream of a tropical Venus, warm and potentially habitable, received its first hard evidence against it. Venus was not warm. Venus was extraordinarily hot. But knowing, even uncomfortably, is better than imagining. The Soviet Union, in the years that followed, launched mission after mission to Venus under the Venera program. Most of them failed, overcome by pressures and temperatures that early spacecraft were not built to survive. The engineering challenge was immense. How do you design a machine that can function in an environment where the air weighs 92 times more than Earth's, where the temperature is nearly 500 degrees? You over-engineer. You build pressure vessels with walls thick enough to withstand the load. You cool the interior as much as you can, buying time. You transmit your data as fast as your instruments will allow, knowing the clock is running. On December 15th, 1970, Venera 7 became the first spacecraft to successfully land on another planet and transmit data from the surface. It operated for 23 minutes, transmitting temperature and pressure readings from the surface of Venus back across the tens of millions of kilometers of space to the receivers on Earth. 23 minutes of data, bought with years of engineering and the knowledge that the machine would not survive. The data confirmed what Mariner 2 had suggested. The surface was extraordinarily hot. The pressure was crushing. Venus was not habitable in any sense. But the measurements were real. The numbers came back, and science moved forward. 12 years later, Venera 13 arrived. It survived for 127 minutes on the surface of Venus, the longest any Soviet lander had managed. In that time, it took photographs, color photographs. The images show a landscape of orange-brown angular rocks, slabs and rubble scatter across a surface tinted amber by the thick atmosphere above, filtering the sunlight. The horizon curves slightly, suggesting the wide-angle optics. The sky above is a uniform, bright, featureless orange. It is one of the most remarkable images ever taken by a spacecraft. A photograph from the surface of another planet, not a distant, cold, airless world like the moon, but a hot, crushing, living atmosphere. The first photograph of Venus's surface in color. 127 minutes. Then silence. The heat and pressure overcame the machine, as they were always going to. But the images remain. The data remains. The orange rocks of Venus, photographed once in 1982, are still the only direct visual record we have of what it looks like down there. In 1985, two Soviet spacecraft called Vega 1 and Vega 2 arrived at Venus on their way to a rendezvous with Halley's Comet. As they flew past, they each released a descent module into Venus's atmosphere. And inside each descent module, instead of just a lander, was something different. A balloon. The Vega balloons inflated in Venus's atmosphere at an altitude of approximately 54 kilometers, right in the middle of the cloud layer, in the relatively temperate zone where temperatures and pressures are closest to Earth-like conditions. Each balloon carried a small scientific payload, measuring wind speed and direction, temperature, pressure, and atmospheric chemistry. The balloons floated for nearly 2 Earth days, drifting on Venus's atmospheric currents, carried around the planet by the high-altitude winds. Their signals were tracked from Earth by a network of radio telescopes. For 46 hours, the world received data from 2 small balloons drifting in the clouds of Venus, the only spacecraft ever to float in the atmosphere of another planet, carried by the same winds that have been blowing since before the first humans drew breath. Then the batteries died and the signals ended, and the balloons drifted on alone in the amber dark, silent, unknown, perhaps still floating somewhere in those clouds today. In 1978, NASA's Pioneer Venus multi-probe mission released 5 separate probes into Venus's atmosphere simultaneously at different latitudes. They descended through 120 kilometers of atmosphere, measuring temperature, pressure, and composition at every altitude as they fell, until they reached the surface and were destroyed. No parachutes, no soft landing, simply falling through the atmosphere, measuring as they went, transmitting their data upward until the impact silenced them, for the 5 probes survived all the way to the surface. One of them continued transmitting for 67 minutes after impact, somehow undamaged by the landing, still functioning in the heat and pressure, still sending back readings from the very surface of Venus. A machine designed only to survive the fall, surviving the landing too, by accident or by generous engineering margin, or by the particular kindness that the universe occasionally extends to careful work. Then came Magellan. NASA's Magellan spacecraft arrived at Venus in 1990 and spent 4 years in orbit, mapping the surface with radar. By the time the mission ended in 1994, it had imaged approximately 98% of Venus's surface at resolutions of between 100 and 300 meters. For the first time, humans could look at Venus's surface in detail. Not a few photographs taken from one landing site, but a near-complete global map. Every corona, every nova, every arachnoid, every pancake dome, every wind streak, every lava channel, rendered in radar brightness a mosaic that covered almost the entire planet. The pancake domes became visible. The coronae took on their full extraordinary shape. The tesserae revealed their complex, crumpled texture. Maxwell Montez rose in the map like a bright fist above Ishtar Terra. The longest lava channel, stretching for 6,000 kilometers, could be traced from beginning to end. In 4 years, Magellan transformed Venus from a planet of mystery into a world we could actually see. Not visit, not touch, but see in more detail than any previous generation of astronomers had imagined possible. At the end of its mission, Magellan was deliberately sent into Venus's atmosphere, where it burned up, a final experiment in the dynamics of atmospheric entry, contributing its last data as it was consumed. The spacecraft that visited Venus were made by human hands, assembled by engineers and scientists who worked for years on machines they knew would be destroyed, who designed probes to survive 23 minutes, 127 minutes, 2 days, knowing the end would come and accepting it, and sending them anyway. There is something in that acceptance that is worth holding for a moment, here in the quiet. The knowledge that a thing will not last is not always a reason not to make it. 23 minutes of data from the surface of Venus is still 23 minutes of truth. 127 minutes is still a set of photographs that will exist as long as human civilization keeps records. The Vega balloons drifted in acid clouds for 2 days and then went silent, But the winds they measured have been blowing for millions of years, and now we know their speed. Nothing built to last forever lasted, but the knowledge remains. Let that thought settle gently, like a craft descending through thick air, giving everything it has while it can, and finding that it is enough. The maps we have of Venus are extraordinary things. The Magellan radar mosaic, assembled from thousands of individual radar passes over 4 years of orbital mapping, shows Venus's surface in its entirety, a global portrait in shades of gray, rendered not in visible light, but in the echo of radar pulses bounced off rock and lava and ancient deformed terrain, the plains rolling wide and level, the volcanic features rising above them, the coronae, the novae, the arachnoids, all visible now, cataloged, named, studied, and alongside it, the elevation maps, showing the dramatic range of Venus's topography in false color, from the low lava plains in deep blue to the highlands of Ishtar Terra and Aphrodite Terra in green and yellow, to the bright red summit of Maxwell Montes standing above everything, the highest point on a world that has been building and collapsing and rebuilding itself for 4.5 billion years. These maps are among the most detailed portraits of any planetary surface in our possession, and they were made by a spacecraft launched in 1989, with computing power less than that of a modern wristwatch, using radar because optical cameras would have seen only cloud. The achievement is still remarkable decades later. Patient work, patient engineering, patient science. We know that the surface of Venus is hostile to everything we have ever sent there. The Venera probes lasted minutes. The most resilient lasted just over 2 hours. The pressure is crushing. The temperature is lethal. The chemistry is corrosive. And yet there is one place on Venus where the conditions are different. At an altitude of approximately 50 to 60 kilometers above the surface, right in the middle of the cloud layer, in the zone where the Vega balloons once drifted, the temperature is somewhere between 0 and 60 degrees Celsius. The pressure is close to Earth's sea level pressure. The sunlight is abundant. It is, by any reasonable measure, the most Earth-like environment in the solar system beyond Earth itself. Not comfortable, exactly. The air is still mostly carbon dioxide. The clouds are still sulfuric acid. But for a sealed habitat, a pressurized shell, resistant to chemical corrosion, floating at altitude, the conditions are almost manageable. Some engineers and scientists have proposed exactly this. Not a landed outpost on Venus's surface, which is clearly impossible with current technology and perhaps with any foreseeable technology, but a floating habitat, a crewed airship, or a series of large aerostatic balloons supporting a habitat, drifting at 55 kilometers altitude in the cloud layer of Venus. The crew inside would experience near-Earth gravity, Venus's surface gravity being 91% of Earth's, essentially unchanged at altitude. They would experience comfortable temperature and pressure. They would be, in a sense, neighbors of the Vega balloons, drifting in the same layer of cloud, breathing recycled air inside a shell surrounded by sulfuric acid, but alive and working and looking out at an amber sky. This is not imminent. It is not the next step or the step after that, but it is not impossible. It is a serious engineering concept, studied by serious engineers, waiting for the moment when the technology and the will align. The sky of Venus, at the right altitude, is closer to home than any other place in the solar system. And the surface of Venus, that remapped, radar-revealed ancient volcanic landscape, is about to receive more attention. NASA's Veritas mission, Venus Emissivity, Radio Science, in SAR topography and spectroscopy, is planned for launch around 2031. It will orbit Venus and map its surface in significantly higher resolution than Magellan achieved, using modern radar technology and spectroscopic instruments to study the composition of the surface as well as its shape. Veritas will look for evidence of recent or ongoing volcanic activity. It will try to determine whether Venus is still geologically active today, whether any of those 1,600 volcanoes are still erupting, whether lava is still flowing somewhere on that amber-lit plain. Preliminary evidence from Magellan data, reanalyzed with modern techniques, suggests some volcanic features may have changed in the years since Magellan mapped them. If Venus is still volcanically active, if lava is still flowing there, even now, it changes how we think about the planet's interior, its heat budget, and the likely timing of the next global resurfacing. Veritas will also study the composition of Venus's ancient tesserae, looking for evidence of past granite, a rock type that, on Earth, forms in the presence of water. If granite is found in Venus's oldest terrain, it would suggest that water was indeed present on Venus in the deep past, that the ancient ocean hypothesis has geological evidence to support it, that Venus was once genuinely habitable. The mission will carry forward what Magellan began: higher resolution, better instruments, decades of improved understanding of what we are looking at and what questions to ask. A new chapter in a very long story. We have come a long way tonight. We began with a light above the horizon, a single bright point in the evening sky, noticed by every human being who has ever walked outside at dusk and looked west. We watched the Babylonians record it on clay. The Maya calculate its cycle to within a day. Galileo see its crescent through a small imperfect lens. We felt the slow inversion of its time. The day longer than a year, the sun rising the west, the year turning over twice before a single noon arrived. We descended through a sky of racing wind and acid rain and lightning and sulfuric cloud. We stood at the margin of a surface that melts lead and crushes spacecraft, that weighs 92 times more than the air you are breathing right now. We walked slowly across its volcanic plains. We looked at its ancient craters and its pancake domes and its coronae and its spiderweb arachnoids. We traced the 6,000-kilometer river of lava, dry now for millions of years, still visible from orbit. We met the spacecraft that visited. Mariner 2, passing at 35,000 kilometers. Venera 7, transmitting for 23 minutes. Venera 13, sending back orange photographs. The Vega balloons, drifting in the amber clouds for 2 days, and then going silent. We wondered quietly whether something might be alive up there, drifting in that same cloud layer in conditions that Earth life could barely survive. And we looked forward gently to the missions not yet launched, the maps not yet made, the questions not yet answered. Venus is still up there, whether you can see it from where you are tonight, whether the sky is clear or clouded, whether the season puts in the east at dawn or the west at dusk. It is there, shining with that steady, brilliant, unchanging light that has been shining above every human night since before we had words for it. It is shining above you right now, 475 degrees on its surface, 92 atmospheres of pressure, a sky full of acid and lightning and ancient wind, and above all of it, that reflected sunlight, clean and white and beautiful, traveling 100 million kilometers across the vacuum of space to reach your sky. You cannot feel it, but it is there. You are very tired now. The thoughts that felt urgent earlier have dissolved, the way mist dissolves when the sun climbs high enough. There is nothing left that needs doing tonight. There is nowhere left to go. Just this warmth, this weight, this quiet room, with its familiar sounds and its familiar darkness and slow, unhurried rhythm of your own breathing. You have spent the night on Venus, in the only way that is safe and gentle and possible, from a distance with curiosity, without urgency. You have let its strangeness wash over you and then recede, the way water washes over a stone and recedes, leaving the stone unchanged but perhaps somehow a little cleaner. Let your eyes be completely heavy now. Let your body sink a little further into the surface beneath you, into the weight of the mattress, the warmth of the blankets, the small familiar constellation of your room in the dark. Let Venus go on doing what it does, spinning its slow backward spin, with its sun rising in the west, with its clouds racing overhead at 360 kilometers per hour, with its surface baking in its ancient heat, with its possible drifting microbes in the amber cloud layer, with its future mission still on drawing boards, with its 1,600 volcanoes standing in the dark waiting for the next great eruption, with its arachnoids and coroni and pancake domes sitting, unchanged on lava plains that have not moved since before the first fish walked on land. All of that is happening. All of it, always, without pause. And none of it requires anything from you tonight. The night is very quiet. You are very still. Venus is very far away and very beautiful, and you have learned it well, and now it is time to sleep. Let the last thought be the lightest one, not the crushing pressure, not the acid sky, not the heat, but the light. That single, steady point of light above the horizon, the one that every human being has seen, the one that was called the morning star and the evening star, and the star of Ishtar and the companion of Quetzalcoatl, the one that Galileo saw as a crescent, the one that the Mayans counted across centuries, the one that rises before the sun or lingers after it sets, patient and brilliant and utterly unchanged by everything that has been thought about it, written about it, wondered about it. Just a light, in the dark, bright and steady and ancient and yours.